So I'd like to start today's seminar with a very short experiment for which I've recruited you all as voluntary participants. So I'm gonna teach you a tiny bit of Finnish. I'm not too afraid that many of you know Finnish. And I'm going to run immediately after a test. So please pay attention. So let's start with a first word, which is university. And in Finnish, this is yliopisto. The second word is data type, pretty important for us. This is tietotyyppi, clearly. And the third one is sauna, which is, this one is easy, sauna, pronounced the Italian way. So, repetita juvent, university is yliopisto, data type is tietotyyppi, and sauna is sauna. All right, time for the test. What is data type? Tietotyyppi. Okay, we need to work on the pronunciation, but that's good enough. What is sauna? Right? What is university? Yliopisto. What is programming? Anyone? It's pretty important for us. That's ohjelmointi, obviously. You can be pretty proud of yourself because 3 out of 4, 75%, that's not too bad. Now, what did we just do? And what does it even mean to learn something? So as I was hinting at in my abstract, we can go to a dictionary and read up a definition of learning. This is one of the many possible ones from the Merriam-Webster dictionary. So it has actually multiple senses in which the word to learn is defined. The first sense is to gain knowledge or understanding of or skill in by study, instruction, or experience. And then there is an interesting second sense. For example, an example of the first sense would be learn to play chess. And then there is like this interesting second sense that is to memorize. For example, to learn the lines of a play. And what we just did with the Finnish words is some form of memorization, right? I tried to show you something in a given context, like these words in Finnish, and then I've checked you mostly on the same context. So training and testing. But that's not really what we hope for as educators. Like the whole premise of our education is that you are being trained, you are learning in some context A, and then later on you're able to display some knowledge in a potentially different context B. For example, there is like this, learn Java so that you will then be able to know how to program in Python. Or if you want even harder, learn Latin because it's going to be helpful for everything in life. That's what we hear every time in Italy, no? And all these assumptions rest on the idea of transfer. This is a key concept in education, and I'd like to show you what we know about transfer. I'm going to start with something very basic that is drawn from basic geometry. So I'm going to ask you again to participate. There is no trick to this question. I'm going to show you now a bunch of triangles, sorry, and I'm going to ask you for each one if it is a right triangle or not. Ready? Here is the first one. Is it a right triangle? Yes, everybody's nodding. Here is a second one. Is this a right triangle? Yes. Here is a third one. Is this a right triangle? Yes, right. What do you think kids say when they do exactly what you did now? Can you imagine what they do? Oh, they say no. Why do they say no to the second and the third? Right, it has to do with some sense of rotation. They say no, and people have been digging into this because every right triangle that the teacher draws in class or that they see on the textbook looks like a triangle of that kind with the axes that are parallel, with the cathets that are parallel to the axis. So this is the context A in which they have been trained, and then they are asked to display knowledge in contexts B and C, and that doesn't really work. And they did a very interesting study. So here are the results. Here are our triangles. They used middle school students. So almost everyone gets that the first one is a right triangle, and then the percentages of the different kids at different ages that they get this problem or not drops for the second, and it drops even further for the third one. And they also checked with teachers and pre-service teachers, like teacher before coming into service, and 100% of them get the first one right. That's a nice consolation, but still not everybody gets the third one, which seems particularly surprising. You know, we're not used to right triangles that look like that. Okay, well, you'll say, well, this is like kids and teachers. What do you want from them? So here is something about a different domain, physics, with college students. Now, this is not an experiment, but it's anecdotal evidence from a professor in the US. So this professor has been giving like some very simple tasks during the course. Here is one that we're going to read together. A ball weighing 3 kilograms is dropped from the top of a 100-meter tower. How many seconds does it take to reach the ground? Some basic problem about gravity, and then there is some distractor information, like the weight of the ball. So this is the context in which people have been trained. And then this is the problem that the professor decided to use on the exam. There is a 100-meter hole in the ground. A ball weighing 3 kilograms is rolled off the side into the hole. How long does it take to reach the bottom? And it turns out that some students are not able to see the similarities between these two problems. And so they are unable to solve the second problem during the test, despite the fact that they have been able to solve after having trained in that the first one during the lesson. And not only they are not able to solve the second one, they come to the professor and then complain. I think the exam was unfair because we haven't had any hole problems in the course. We only did tower problems. So the professor was kind of trying to make the teaching engaging, trying to give concrete instances to the students, but then they hooked onto a completely accidental aspect of this problem, the fact that it's a tower, and then they know that they studied tower problems and not hole problems. So this is pretty depressing. But maybe this is just like, you know, math people, physics people. We don't have the same problem in programming, maybe. Now, as some of you may know, part of my research has been developing this approach to teach programming with graphics. So here is an example of a piece of Python code that uses the library we developed, Pytamero, to draw something very simple. It creates a square, a yellow square, and then an equilateral red triangle, and then it puts them one above the other, and then it shows the resulting graphic, which looks more or less like this. And the whole approach that we developed is essentially an approach in which students can learn programming with graphics. They can draw starting from very simple graphics all the way to slightly more complicated graphics, such as the Swiss flag, the barcode, some repetition like a flower, Pac-Man maze, and the iconic Swiss railway clock. So, okay, this is all great. The students love this, but what people wonder really is, well, but do students really learn programming skills if they use Pytamero? Now, I'm going to try to rephrase slightly this question, like to its essence. The question really is, will my students be able to transfer programming skills that they learn with graphics two other domains? That's really the essential question, right? That's what we would like them to do. And now the evidence for programming is also not great. People have been having these claims for years. These are all studies from the 80s. They said, well, logo with its turtle graphic, it's going to be great for the kids. They had like one group of kids going through a year-long program in which they learned programming using logo. And then the year after, they compared this to another group of kids who didn't use programming, who didn't learn programming. And then they did a test on planning skills. Like, oh, maybe if you program, you need to think about what are the solutions, so you're developing greater planning skills. And it turns out that, well, the students who did a whole year in programming did not do any better than the other kids on this test. So that's pretty sad. But maybe one can claim, well, but I mean, you know, this planning skills, it's such an abstract thing. And then this is what we normally classify as far transfer. Like we have like these two contexts. They are very far away. It's hard to achieve transfer on that. But it doesn't stop there, unfortunately. Here is another example of a student. So she was able to use the repeat command. This is again logo. It's some kind of construct that you can use as an imperative for loop to repeatedly print her name. And then they wanted her to use the same repeat command to draw a square for the 4 sides of the square. And still she wasn't able to do this. So this is supposed to be a much easier case of transfers. What in literature is known as near transfer. No, you have like these two problems, these two tasks, and they are what they are called isomorphic. Like there is a deep structural similarity between the two tasks. They are not identical, but there is like this deep structural similarity. And we would like to be able to do this. And when we designed the Paitamero, part of our goal was indeed to enable this kind of transfer. And so we said, well, we are going to design the library very carefully such that when people do a task in Paitamero, then they can, at least on an isomorphic task, translate and transfer what they learned. So I tried to verify while I was in Finland last year, this hypothesis in an experiment. So we had one group of students who learned a little bit of programming with Paitamero. So they did very, very basic stuff. Here is a piece of code as an example. Then learn that, oh, you could actually nest function calls. For example, you could nest the creation of a rectangle inside a rotate, and you would get back this graphic. We had another group instead that learned how to program with turtle graphics as a kind of control group. Now in turtle graphic, the functions are really procedures, so you can't really nest them. And so we had some kind of alternative task in which they see and they were observing how the different commands were behaving. And then I said, well, let me check whether the Paitamero group who saw the nesting of functions actually does better in a post test. So I had a kind of multiple choice questions similar to this here. I'm going to show you the simpler version. Piece of code in which you have like the square root of 16, and then I'm doing the square root again of that value, and then I'm printing out the answer. And I'm asking, is this the same? Can I also refactor this piece of code to this piece of code, just nesting these functions? And you would hope that the Paitamero group does better, but it actually doesn't. There was no statistically significant difference between the two groups. And this is not just one isolated fact. Unfortunately, there are more failures of transfer. Here are a bunch of examples. In the training part, the Paitamero folks saw how to place two houses one beside the other, the same house. And this was meant to teach them that you can actually use the same variable multiple times within an expression. That's totally fair. And then we ask, well, can you actually do that? No difference between the two groups. The Paitamero folks do not perform better than the turtle ones who did not see that example. Or we teach them, look, there are functions with two parameters, and you need to pay attention there because not all functions are commutative. For example, if you do above, ground floor, and roof, that's not the same as above, roof, and ground floor. And then in the post-test, I tried to ask an isomorphic problem, saying, well, suppose that you have like this subtract function that does what exactly you would imagine, and I'm calling this with 10 and 7. Is this any different from calling subtract from 7 and 10? And both groups perform rather well, but we don't see an advantage of the Pythamaro group over the turtle one. As yet another example, Pythamaro has a parameterless function that you can use to create an empty graphic. This is meant to show that, well, functions without parameters also exist, and you still need parentheses to call them. Fair. Then in the post-test, I'm asking, well, what if you have like this fake random function? Does this work? Is this legal? And then again, no better performance of the Pythamaro box. So that's pretty sad evidence, but let me try to give you a conceptual schema for how transfer is supposed to happen. Well, we have like these two concrete tasks in two different contexts. And then we have our abstract concept that we're supposed to teach. Like, for example, I want them to understand that you can actually nest calls to functions. And then we would like students to kind of map directly here from task A to, or task in context A to task in context B. But that's not actually how things work. What works is really that you need to form some kind of mental model from the concrete task that you saw in the context A all the way up to the abstract concept. And then you should be able to apply this in the test phase to the context. Now, some of you here in the room may think, well, but this is looks like just a lot of work for this transfer. Can't I just start from the abstract concept? I'm going to teach the abstract idea first. And then once they get the abstract idea, well, they can apply that idea to any concrete task. Now, there is plenty of evidence that this doesn't actually work as we hope. And the reason is people have an hard time acquiring the abstract concept in the first place. And if for you all, this doesn't seem a problem, well, let me bring it out for you. You're special. You're a specially selected group of people for which reasoning with abstract things may come easier than the general population. So back to our transfer diagram here. What really is needed and what we didn't do consistently probably enough in our experiment is to explicitly highlight this relationship. It's not enough that you show them this concrete task and you have in mind that there is an abstract concept, but you need to highlight this relationship explicitly. How do we do this? Well, there are a bunch of ways that we know from the educational literature. One is to use what is called concreteness fading, like gradually removing concrete details until you end up with the abstract concept. Another one is using and presenting multiple contrasting cases, so not one just concrete task, such that they can try to see the differences. And the third one is exploiting what is known as semantic waves. So you kind of move up and down between the abstraction levels. And so you don't just go up, but you see, okay, now that we did the up part, we can go down and maybe back up multiple times until they actually seem to get it. So, okay, this was a lot about transfer. We can easily, though, achieve the illusion of learning. That's very easy to achieve and easy to demonstrate. That's what we did at the beginning with the Finnish experiment. I said, well, look, I'm training you on context A, and then I'm testing you again on context A, maybe a little bit different, so A prime maybe, and then you get like 75%, which doesn't look too off. It's not 100%, but then this is a problem known as teaching to the test in the educational literature. And we justify kind of teaching to the test because we want students to know certain things. Like it's okay to memorize that yliopisto is the Finnish word for university. That's fine. But as soon as the context changes slightly, if you're not learning any rule, you can't really apply what you have learned. And just very quickly, this is not just a problem in the educational literature. Many of you do experiment here and maybe even experiment in machine learning. You're training your model in some context. And well, then if you use like the same context in which you're to check whether the model actually works, well, that's maybe known as this overfitting problem and everything that surrounds that thing. So let me wrap up. We saw the two different facets, if you want, of learning. One is this idea of memorization, and the other one is the idea of transfer. And what I've been trying to argue here maybe is that it's more of a spectrum. There is no clear cut from memorization and transfer. And even more, if you break it down into near transfer and far transfer, it's hard to see if I'm changing just slightly the context. Is this still memorization or it's already near transfer? And then where is really the boundary between near and far? So it's really a spectrum. We can see very clearly the two extremes. So at one extreme, we have memorization that is quite easy to achieve. I've already taught you successfully 3 Finnish words, but it's also quite limited. And then at the other hand of the spectrum, you have something that's extremely hard to achieve, and we have seen that from research, but potentially very powerful. So what I'm trying to argue here is that in our teaching and our research, we do already a lot of memorization stuff, and we should try to push things a little bit more towards at least near transfer.